Something we always need to ask ourselves when we're using methods of estimation is how accurate is our estimate? And in order to figure this out, we need to calculate the error. So if you go back to the original function, the square root of 1 plus x, we don't know what f of 0.02 actually is, but we know that the linearization is a really good estimate. So this is our estimate. And if we get out a calculator and actually figure out the value here, our actual value is 1.00995. Okay, so if we're going to figure out our error, we need to do a little subtraction here. So our error is the difference between these. It's our actual value minus our linearization or our approximation. And we just want the magnitude of that difference. We don't care if it's positive or negative, so we're going to take the absolute value of that. So if we're looking at our values right now, what we're going to do to calculate our error is we're going to take 1.00995 and we're going to subtract 1.01. And when we take the absolute value of that and actually do the subtraction, what we're going to get is 0.000049506. Now I've got a lot of decimals there. Let's write this in scientific notation because this is a little bit annoying. So we get 4.9506 times 10 to the negative fifth. So what this means is our accuracy is actually good to 1, 2, 3, 4 decimal places. I don't have any error until the 5th decimal place. So we can say that our error is less than 10 to the negative 4th. Okay, and you can get that in two ways. You can look at the number of zeros you've got. We're accurate to 10 thousandths. Or you can also look at your exponent here on your scientific notation, and you have to add 1 to that because the 10 to the negative fifth includes that error there in that spot. So we're pretty good here. We're close using our linearization, which we could have done a few hundred years ago without any calculators, and we're really, really accurate. Now we know we're really accurate because we already calculated that our error is less than 1/10,000th, but we want to know if our estimate is too big or too small. And to do this, you need to look at the concavity of your original function paired with the linearization that you have. So if you think about what we did, we found the linearization at x equals 1. We found the equation of this tangent line. So if you think about it, because the line is tangent to the curve and the curve is concave down, our estimate at 0.02 is going to be slightly too big. So if you look down at the graph I have here, here's our linearization. We already calculated it, and if you look at the graph here, this is kind of a nice picture of what's going on. If you kind of look at this box, it looks like our linearization is really good until we get to about right here, and then the line starts peeling away from the curve. But within this yellow box that I've drawn, our line and our curve look very, very, very close. So it looks like our linearization is probably pretty good for values from negative maybe 0.8 to about 1. And I'm just eyeballing here. It kind of depends on what you want your error to be. But once we get outside that, our error starts to become very big. Out here, the error is going to be huge. And out here, our function doesn't even exist. But here at -1, our error starts to get a little bit big as well. So if we look at the concavity of our graph, and we can do that by looking at the second derivative, we can know without actually looking at the graph if our estimate is too big. So if we take the first derivative of x, which I know you know how to do, and we actually already did it when we calculated the slope, we get this. And if we calculate the second derivative, we're going to have that 1/2 constant times, using the power rule, -1/2 times the quantity 1 plus x to the negative 3 halves, and then we have to take the chain rule, and the derivative of this inside is just 1, so I did kind of ignore that up here. So when we get this all figured out, we have negative 1 over 4 times the square root of the quantity 1 plus x to the third power. So this is our second derivative. And if we want to know the concavity of our graph at 0.02, which is where our estimate was, we don't actually have to do the calculation. We just have to decide if that's going to be positive or negative. If we put 0.02 in for x, the denominator will be positive and the numerator will be negative. So we're going to get a negative value for our second derivative, which tells us we have concave down. Okay? So what that tells us is that our linearization is an overestimate for the actual value of the function. So let's draw a few pictures of what's going on there. What we know is we have an overestimate if our function is concave down, because this is what's happening. Here's our linearization, our L of x, and here's our function, our f of x. So we have an overestimate. Our linearization is going to be an overestimate at an a value if our function is concave down at x equals a. Okay? And it's going to be an underestimate if the opposite happens. So if we have a concave up function, and I'm going to call this one g of x, and we have a linearization that happens like this, and I'll call this L of x again. Right now what we get is we get an underestimate. If this is our a value, we're using our linearization as our estimate, but it's below the actual value, so we have an underestimate if f of x is concave up at x equals a. And we've already done this, so you know how to investigate. Make sure all of this makes sense to you, and if you're looking in your book, go through a few examples, do the assignment, and shoot me an email if you have any questions. Good luck.